This is a video on combinatorial coding part 2. Before we get into combinatorial coding, I'll just look at binary search. That's what is actually encoded as a binary number. It's a binary search of over a particular range of values, which is a power of 2. Now, in binary search, we start off with the middle number. Then if the number we are looking for is greater, assuming that this array is ordered, we move to this and then we move to this if it's lesser, and so on. So reducing the bounds till we hit the target. This thing can be improved. For instance, we can make it a ternary search. What do we do? If n is the number of elements, roughly n by 3 to n by 3, we make two comparisons. So depending on that, we can choose one of these three parts in which to perform that. Just as for binary search results in a log based 2 of n is the size of the array. For a ternary search, again it will result in log of n to the base 3, and so on. You can keep increasing the branching factor. It is nothing but a tree search only. Now here, this is what we can use the same technique here. Now I'll give you a rough general idea. You can make improvements to it. What happens is we have an R combination of n. There are n bits here, of which R of these are 1. Now the smallest number which has R ones in it is this. All ones here are ones, and n minus R zeros here. Okay, and the largest R number having R bits in it is here R, and the n minus R, which is here. Okay. Now what we can do is, if we take the basic binary case, again, since for R equal to n by 2, there are nearly 2 power n minus 1 of those, the space will be very large. So what you can do is, now suppose you take the midpoint of these two, some number you will get, but it will not have, it may or may not have R ones in it. If it does not have R ones in it, you can apply some kind of a heuristic. Now you can either use a branching factor of 2 only, if we suppose we take, and we get an average number here. What we do is, we could try either directly comparing it with this number to see whether we are looking for something which is closer here. And then what you can do is you apply a heuristic, so that now this number itself will not have R1s in it, but you are only interested in those numbers which have exactly R1s in it. So you make changes to it if the number of ones in it is less than R. You increase it in such a fashion so that it can be, if you always choose the number closest to this which has R1s in it, then again, because there are so many of these, the branching factor, you will still not gain much data compression while trying to code it. So you'll have to apply a heuristic and cleverly choose between several of these, so that your some mid value between this and this, but which always has R1s in it. Now if you are using a binary search, what you can do is you can come up with two numbers somewhere in between. In this case, you will have to take this and this by, say, divided by 3, and then you'll have two numbers, 2n by 3. So apply heuristics to both of these to come up with two numbers which are close to this value, whose value is this. So then you'll be able to cut it out in one third, meaning that you're now interested in all those R combinations which lie between this and this one, or this and this one, like that. So what you are doing is you are applying the same binary search or ternary search or quaternary search or pentanary search and so on, but you are doing it only for numbers which have R1s in it, since you are interested only in R numbers which have R1s in it. So you could go about that way. For ternary search, for instance, you could do this. For, let us take a simple case where R is equal to n by 2. This is most of this will be this, right? So what you can do is you can take the two numbers you take are alternate ones and zeros like this, say for n by 2, half of them ones and zeros. The other number will be this. Now if you have a branching factor of 3, that is you already have two numbers, so you can check, you can go either between all 0 or all 1s here and n minus r zeros here, or all 1s here. So you will have 3 intervals here in which to check for r. Like that you can increase the branching factor and apply a heuristic or some simple method by which you try to hit the target as fast as you possibly can. This is another alternate way of approaching combinatorial coding, so that you are able to. This is not a very bad idea, provided you are able to make the right guesses really fast. And instead of arithmetic mean, you can again here, the inequality arithmetic mean greater than or equal to geometric mean greater than or equal to harmonic mean. Right? So what you can do is that, so if you are using a ternary, means your coding will have to be on base 3. If you are using quaternary, base 4. So you can use a slightly higher base, but try and hit the target as fast as you possibly can by applying a simple heuristic. Now so what this does is, what thing is, we have to, any idea when we have, generally when we come up with ideas, what I have usually found is that the vast number of ideas will be very bad ones. There, for instance, of the stuff that I have done, worked it out on paper, and I was rummaging through it more than once, and a lot of it is still left. But what I found was more than half of it were really very, very, since discardable. There is nothing in it. Out of the half, more than half, say 50 to 60%. Some of them are worth looking into, I said, and I kept it aside. Now, among those worth looking into, I found, again, this was 60% of what I discarded. Of the 40% that remained, another 60% were worth closely looking into. And within that, some of them were slightly really good ideas which work. In other words, just like in the outside world, in the world of ideas as well, the vast majority of ideas are pretty not very helpful ones. Only a small minority of them are worth taking a more closer look. Those within those will be worth more taking an even closer look. And finally, some of them will be extremely good ones. So hitting this is not easy. You will have to. So this kind of sifting has to take place even in the world of ideas as well. So just as in the outside world, there's always the amount of specks of light are very, very few. Of those, the really bright ones will be much more fewer, and so on. So also in the world of ideas also, the vast majority of ideas or thoughts that you have will not be very good ones. A few of those will be good, and among those few will be better, and among those some will be really excellent ideas. This is true of most. So when you come up with solutions like this, now for this one, for instance, it is not perfect, like I said, because for r equal to, but it allows for the possibility of improvement in the sense that you can apply a heuristic or some guiding post there for the choice of the next r combination which you're trying to hit, so that you come as close to it as possible. So any idea that allows for the possibility of improvement in itself, which has an inherent characteristic of being capable of being improved upon, and also allows for the possibility of generalization. Those ideas will be the right ideas when you try to solve problems in computing or any other area where the same principle can be generalized. That will afford for general improvement, and where it allows for other possibilities to take place there. So such ideas, general ideas, which open up possibilities and allow for generalization, are generally the better ideas. Those which are tend to be very restrictive and very confined, very narrow, will have very little room for improvement or little room for betterment and little room for instance, here the possibilities here are quite a lot, isn't it? So that, like that, you'll have to come up with very specific ideas. Generally tend to be very limiting, because those ideas which allow for improvement generally tend to be, which can be generalized from a specific case to a, you can always start off with a specific case, but you can generally, a specific case is a specific solution of a more general solution. If you can try and hit upon the more general solution, that is always better. Some of them